Okay, we're going to continue on here, chapter 13, I think. So last time we got into really chapter 13, and we're talking about, again, chemical equilibrium here. And as we talked about, chemical equilibrium really does revolve around a specific type of reaction, which are those reversible reactions, those ones where we have the arrows heading in both directions. And that means obviously there is a forward reaction, which is heading in that direction, and there is a reversed reaction, which as you make enough products, eventually they will come back together and really kind of make our reactants in that case. And remember, as we talked about, when we do reach chemical equilibrium, what that really means is we're talking really about the rate, kind of like what we were talking about in kinetics, is the rate of the forward reaction will equal the rate of the reverse reaction. And really what that means is it does not necessarily mean that we have equal amounts of everybody on both sides of the arrows, but what it means is wherever everybody is when it reaches chemical equilibrium, in terms of their concentration, if it's pressures, if we're dealing with pressures because we're dealing with gases, they basically will maintain where they are at, because just as quick as it sort of breaks apart into products, it will kind of recombine just as quickly back into reactants. So it's basically a nice equilibrium of where everybody, I'm gonna spit that out, right? Where everyone is at that point, will basically just kind of maintain where they're at. And they'll be able to maintain where they're at regardless of what happens, unless you do something to really screw up the equilibrium. But if you don't do anything to it, it'll be able to maintain exactly where they're at that point. Again, it may look like there's nothing much happening when a reaction reaches equilibrium, but again, if you sort of super zoomed in there, there's a lot of activity, guys going forward and reverse in that reaction to maintain the equilibrium. There is a relationship that's known as equilibrium constant, which is K, where we basically take our products, concentration of our products divided by the concentration of our reactants. Remember that when we do calculate the equilibrium constant, we do take the coefficients into account. So if this was, say, a 2 and a 3 and a 2, we would write the equilibrium expression for that, which is C times D squared divided by A squared and B cubed in this case. Again, taking into account those coefficients here is obviously 1. When we do write it in terms of concentrations, the K value is sometimes referred to as the Kc value for concentrations. If we have a reaction that deals with gases, so oftentimes with gases, we do follow the pressure of what's going on. We can write an equivalent sort of equilibrium expression, which deals with pressures, and it would still be the partial pressure of our products, still taking the coefficients into account, divided by the partial pressure of our reactants, once again, taking those coefficients into account. And that's what's referred to as the Kp value. Both the K value, Kp, Kc, any K value is really the same. They all have like little subscripts next to them, and they all sort of apply to different sort of situations. But ultimately, they're all calculated the same, which is products over reactants. When we talk about K, it is just a number, and it is capital K, by the way. Again, lowercase k is our rate constant. It is just a number. And what that number tells us usually is what we could expect to sort of be there when we do reach equilibrium. So if we have a large value of K, that means that we mainly would expect products to be there at equilibrium. And if we have a small value of K, we would mainly expect reactants to be present at equilibrium in this case. What is a large value, a small value? Remember that anything sort of above 1 is considered a large value. Anything less than 1 is considered a small value. So if you see something with a negative exponent, it's considered small. If something, kind of a positive exponent or kind of whole numbers, would be more of a larger one. We typically do not use units with the equilibrium constant. It is just, again, a number. There's really a couple of things that we put into the equilibrium expression that and there's a couple of things that we really don't. Really, when we write the equilibrium expression, only things that are aqueous and things that are gases are included, because they are actively sort of involved in what's going on, the reaction, the equilibrium. We do not include things that are pure liquids or solids, are not included. And we finished up, I think, also talking about a relationship of how you go from, say, Kp to Kc. Now, in certain problems, you may be given enough information to calculate the Kc value, but you may need the Kp value and vice versa. So there is I believe Kp is equal to Kc RT delta N. These are our equilibrium constants for pressure, equilibrium constant for concentration. That is our gas constant, which is the same one that we use in the ideal gas law. That is our temperature in Kelvin. And as we talked about last time, it's really important when you do the delta N part of that you do take products minus reactants. So that's the N of the products minus the N of the reactants. And those are just of the gas molecules. So those are the change in the moles of gases. So anybody with a G on either side of the arrow, that is what you're looking at here. Any questions on any of that stuff there? I think we got into last time. Okay, so I think we did a example, I think, where we ended up. So I think we did this one, yeah. That's where we finished, I believe. Yeah. All right, so then let us do this one next. The equilibrium constant Kp for this reaction is 158. What is the equilibrium pressure of O2 if the partial pressure of NO2, and again, on your paper, it may not specify, we'll do the first guy as NO2, is equal to 0.4, and the partial pressure of NO is 0.70. That's what you have on your paper, or you don't have it on your paper? So we'll go with NO2 for the first one there, is 0.4. Look, so obviously in this case, we're given the Kp value. We got some pressures, and we're actually looking for a pressure here. So Kp expression would be a good place to start. So that's going to be our products, which in this case is the partial pressure squared of NO times the partial pressure of O2 divided by the partial pressure squared of NO2. And that's going to equal 158, which was given to us right there. At this point, we have mostly everything except for O2 here, which is what we're looking for. So we can really plug everything in. And if we did that for NO, we went with 0.27. So that's going to be 0.27 squared times the partial pressure of O2 divided by our NO2, which is 0.4. And we're also going to square it, equals 158. So we're basically going to multiply that to the other side and then come back through and divide there by what's on top. And if we do that, we will end up with 158 times 0.4 squared divided by 0.27 squared. And that would give us a partial pressure of O2 of about 347 atmospheres. It would need units because it is a pressure, and it would be obviously the same units as the other pressures that we see here. Any questions on that there? So the value of K here is a large value, which means when we reach equilibrium, we would mainly expect to have products, right? And that would make sense here. We have a pretty large pressure for O2, which means we made a lot of O2. Otherwise, it wouldn't be able to make all that pressure. Any questions on that one there? All right. So we sort of talked a little bit about it earlier, but just to officially talk about it here, there is heterogeneous equilibrium. And in a heterogeneous equilibrium, we have everybody in different states, or there are different phases, I guess is a way to put it. As we talked about if there is a solid involved, it really is not going to be able to participate. You could kind of think of it like it's just kind of hanging out. In order for it to be able to participate, it would have to dissolve, and at that point, it would be an aqueous ion, and then it would be included. But as a solid state, it would not include. So those are constant in this case, which means when we do get to sort of our equilibrium constant expression, we would not include those guys. So those guys would not be included, which means the proper equilibrium expression for this one would be the Kc is equal to just the concentration of CO2 in this case. And because CO2 is a gas, we could also write a Kp expression for it, which would be the partial pressure of CO2 in this case, would be it. So as we talked about earlier, any solids or liquids do not include. And again, that pretty much leaves us our aqueous and our gases should always be included in the equilibrium expression. And that's sort of what we see here. You know, the solid is just sort of sitting, if you will. It's not necessarily participating. These guys are actively moving around and sort of participating in this particular equilibrium. All right. So let's take a look at another one here. Consider the following. The partial pressures of each gas is 0.265. What is the Kp value? And also what is the Kc value at 295 Kelvin in this case? So in this case, we're again looking for both the Kp and the Kc. We are given the partial pressures, so it would obviously make sense to start with the Kp since we do have the pressures. So we're going to write our Kp expression here, and our Kp expression will be the partial pressure of NH3 times the partial pressure of H2S, and am I going to include this guy? I am not. Again, it's a solid, so it does not go in there. So that really is our expression. In this case, both of them are 0.265, so basically we're squaring it there. And that would get us 0.265 squared. And that would give us a 7.02 times 10 to the minus 2 Kp value in this case. Any questions on that? Yeah. No, in this case, all we need to calculate the Kp is just the partial pressures of everybody. Other questions? Now we will use the temperature here as we need to now convert our Kp into our Kc value, and we would use the equation that we saw earlier. So in this particular case, the temperature is already in Kelvin, so we're good to go on that. We do need to calculate our delta N, and in this case, again, we want to do products minus reactants. So that is 1 gas molecule, 2 gas molecules minus no gas molecules, right? So 2 minus 0 is 2. So our delta N in this case will equal 2. And I think we might be okay on that. That's going to give us 7.02 times 10 to the minus 2 is equal to our Kc. That's going to give us 0.08206 or 21 if you like that number better. We got our temperature already in Kelvin, and we're going to square it. Remember that you do want to do this math first before you square it. So you want to do what's inside there, 0.08206 times the 295. And then we're going to square it. So you get something like 24.2, and then you square it. That will give us something like 586.01. To finish it out, we then would take that and divide it over to the other side. And that would get us 7.02 to the minus 2 divided by what we got there. Looks like perhaps our Kc here will be 1.20 times 10, 1, 2, 3, negative 4 in this case, looks like. Any questions on any of those there? Yes. Where did I get the N? The N is the difference in the number of moles of products minus reactants. I'll get that right. So on our product side here, we have 2 gas molecules, and on our reactant side, we have none. Basically, it's all solid. So we basically take products minus reactants. Other questions? Yeah, so that's how you could figure out. You just basically go to anybody that's got a G next to it, and then whatever the coefficients are is basically how many moles you have, right, of each of those. Those numbers in front represent the moles, right? Or they could represent molecules, but in this application, they represent moles. Yeah. Other questions? Yeah. Yeah. Yeah, so delta N is the number of moles of gas molecules, basically. Yeah, it's only gas, yeah. And that's if you kind of look at this stuff here, this is all kind of like ideal gas type stuff here. So this is all basically related to gas laws and stuff like that. So it's all involved about the gases, that part of it. Other questions? Okay. All right, so let's talk about a couple of other things that we do with the equilibrium constant value that sometimes does come up. As we talked about a little bit earlier, I think maybe when we were talking about mechanisms, for example, not all reactions do occur sort of in a one-step process. Sometimes reactions are a sort of combination of multiple individual reactions. And equilibrium reactions or reversible reactions are no different. So when we sort of add reactions together or sort of manipulate equations that have equilibrium constant values with it, we do have to adjust the actual equilibrium constant value. So for example, here, if we took these two reactions and we added them together, we would get this overall reaction of A plus B goes to E plus C, with our C's canceling and our D's canceling in this case. Again, anything on opposite sides of the arrow will cancel out or reduce down. And if we were to write the equilibrium expression for our overall guy here, it would be K is equal to the concentration of E times the concentration of F divided by concentration of A and the concentration of B. How that is really achieved, if we look at the individual ones, so that's for the first step there, that's for the second guy, is actually if we multiply these together, these guys would cancel, and that would leave us the actual equilibrium expression that we are looking for. So one way that we sort of manipulate a reaction is if we have to add up a number of individual equilibrium reactions, and we're looking for what is the K value we get at the end there when we sort of add everybody together, we basically will multiply the K value. So that's a little bit different than what we do with like delta H, where we add them together. Here we do multiply the K values if you need to sort of manipulate it. Now, another very common thing that occurs is sometimes we may need to actually reverse a reaction. So the way it's written may not be the way that we actually need it. We may need our reactants on the product side, products on the reactant side. So another sort of way that we manipulate a reaction is to actually reverse the reaction. And when we reverse the reaction, what we are essentially doing to the K value is taking the inverse of it, or 1 over the K value. So if we look at basically this equilibrium expression for this reaction above and the one here, they are basically the inverse of each other. So if you were to reverse a reaction, unlike delta H where you would change the sign, for a K value, what you do is take 1 over the K value, and that will give you the actual value for the specific reaction you're looking at. When you do see a K value, by the way, it is specific for exactly how that reaction is written. So for example, if I would say the K value is 216, it is specific for that reaction written exactly like that, with NO2 being our reactants and 2O4 being our products. Now, as opposed to if I said the K value is this number here, that is specific for exactly how this reaction is written. What are our reactants? What are our products? So when you see a K value or it's given, it is specific for exactly the way the reaction is written. And that's, again, a very common way that we will sort of manipulate an equation. A couple other common ways that we sometimes will need to sort of manipulate some equations are, for example, if we had an equation like this, A plus B goes to C plus D, and say the K value is like this. If we write the expression here, it would be C times D divided by A times B. Now, let's just say, for example, we needed not 1A, but we needed, say, 2. We would then need to take this reaction and multiply it by 2. And if we did that, that would give us 2A plus 2B goes to 2C plus 2D. And if we wrote the equilibrium expression for that reaction, where we basically just distributed a 2 to everybody, we would get the concentration of C squared, D squared, A squared, and B squared. So what occurred in terms of the equilibrium constant as I multiplied by 2? What happened to the equilibrium constant value here? It was squared, yeah, because I multiplied by 2. If I were to multiply by 3, the equilibrium constant value then would be cubed, yeah? So if you need to multiply by a common number, how that affects the equilibrium constant value is basically you take the equilibrium constant value to whatever that number is. So if you we multiply it by 2, you square it, you cube it, is times it by 4, you take it to the 4th power. The other thing that's also very common that sometimes you need to do is basically maybe you need to divide by a common number. So if I started with this reaction, I decided I needed to get rid of 2 all the way here. When I do that, that would take me back to the original equation. And as we look at the K value starting here on the bottom, but ending at the top, what is the difference between those two? That is the square root. Yes, if I take the square root of it, I end up with the guy on the top. I could take the square root because I basically divided by 2. If I divide by 3, I would actually take the cubed root. Yeah, so if you need to multiply an equation by a number, you basically take the K value to that number, basically, is how it changes. If you need to divide by a number, you basically take the root there to that number, whatever you may divide by. So those are the 4 sort of common ways that we sometimes will have to manipulate equations that involve equilibrium constant values. If you add equations together, you actually multiply the K values. So that's a very common error a lot of people make. They end up adding because they think, it's kind of like H, you just add them. So you do multiply them. If you reverse a reaction, you take 1 over the K value. If you need to multiply by a common number, again, you take it to that common number. Or if you need to divide by a common number, you would take it to that common number there, or take the root of it to that common number. So let's take a look at maybe one here. Let's say we had A plus B goes to 20. And let's say we have and let's say we wanted let's say we wanted so what would the K value be based on these guys up here for this reaction? I hope I did it all right. I didn't mess up, but we'll see. All right, so figure out what the K value would be on this particular one here. Okay, let's take a look. So again, whenever you're building equations, as you might have been taught when you did some Hess's law stuff, really the simplest approach is the best, just to make sure everybody's sort of on the correct side of the arrow and make sure that you have the right amount of everybody on both sides. So here I got A on the left and I got A on the left. So that looks good. I don't really need to do anything perhaps to that first equation. So I'm just going to rewrite it the way it was. And because I really didn't do anything to it, the K value obviously would remain the same in this case. Now, when I look at E, it's on the right-hand side, but in our equation up on top, it's on the left, which means we definitely need to reverse it, right? And in addition, we don't need one E, but we need a couple of them. So we also need to reverse the reaction and also multiply by 2. So if I do that, I'm going to multiply this entire thing by 2 and reverse it, basically. All right. So if I do that, that will give me 2C plus 2D goes to 2E plus 2F. So now I need to keep track of what I did. So my original K value was 15. I reversed it, which means I should take 1 over the K value. So I should take 1 over 15. And I also multiplied by 2, which means I then should square it as well, right? So those are all the things that we did to it. So now what we have here, if we did this correctly, is we should be able to cancel out the C's, cancel out the D's if they're on opposite sides. Everybody on the left stays on the left, everybody on the right stays on the right, and we did hit the same equation that we're looking for. Now, in terms of 1 divided by 15, and then we're going to also square it there, that's going to give me basically here, go up this way. It's going to give me 0.00444, a bunch of 4s. Now, this is say K1, this is say K2. To get the K value for this guy, once again, we're going to actually multiply those numbers together. So not add, but multiply. That would give me 20 times 0.00444, a bunch of 4s, times it by 20. Gives me a K value here of, we'll call it 8.9 times 10 to the minus 2 in this case. Yeah. Any questions on that one there? Yeah. Yeah, in this particular case, I actually had to do 2 things to it. So for that bottom equation, I had to reverse it. So once I reversed it, if I do it kind of step by step, what that did to the equilibrium constant would then make it 1 over K because I reversed it. And then the next thing I did is basically I needed to multiply the entire thing by 2. And when I multiplied it by 2, what that essentially did meant that I needed to also square it as well. So in this case, we actually had to do a couple of different things to it. And the important thing is to keep track of obviously what you did to it so that you could adjust the K values. I had to reverse it because this was the desired equation here in the middle that's in the box. And I wanted E and F on the product side. And here it's obviously on the reactant side. So I needed to reverse it to get it on the correct side. And that's really the basis of it. Sometimes people get a little crazy when they're trying to add a bunch of reactions together. They make it more complicated than it has to be. It's a very simple idea of just simply, I got to get everybody on the right side of the arrow, right? And if that means the only way to get somebody to switch places is to sort of reverse it. And then you also just need to make sure you have the right amount of everybody as well when you do that. Yeah. And usually in these type of situations, as you're maybe manipulating one or something like that, everything else will kind of fall into place in terms of what else needs to be adjusted. Like here, when we multiplied the E by 2, it also took care of the F, and also the C and the D took care of that. So it properly canceled out as well. Other questions? All right, we will lay it up there, I think, for today.